Sixth.
Yeah, 6B.
Yes.
Okay. So, in an experiment to measure the half-life of a radioactive source, the activity of the source was measured at regular intervals. The results are shown below. Before the measurements were taken, the background activity in the room was measured. So the background activity was 2 counts per second. Okay, so explain how the activity of the source is corrected for background activity. Like they take the background activity away from the activity.
Okay, so explain how the activity of source is corrected by background activity. Okay, so what's your answer?
They take away background activity from the activity of the source.
Yes. Okay, now part second.
Um,
Yes.
Complete the table by adding the values of the corrected activity of the source. Okay, so 120, 60, 30, 15, 8, and 4. So number 3, um, using the grid opposite, plot the data from the table above and draw a smooth curve from through the points. Okay. So at 2 hours, at 0 hours, the activity was 120. At 2 hours, the activity was 60. 4 hours, it was 30. 6 hours, 15. Um, at at 8 hours, it was 8.
Yes.
And at 10 hours, the activity was 4. And a smooth curve through the points. Okay. Using the graph that you've drawn, determine the half-life of the radioactive source. Okay. The half-life of the radioactive source. So the half-life is the time taken for the radioactivity of a source to reduce by a half.
Yes,
So
yes.
yeah, so um the source's original activity was 120, and so half of it would be 60, and so it reduced by half at 2 hours. So that is the activity of the source. The half-life of the source, 2 hours.
Yes, that's correct.
Okay. Um, 5. Using your value for the half-life, calculate the corrected activity of the source 4 hours before the experiment began. Okay. The corrected activity of the source 4 hours before the experiment began. Okay, so every 2 hours it reduces by a half. So um so 2 hours. So at 0 hours it was 120. So 2 hours ago it would have been double that. So 220, 240.
Yes.
Um, and so life equals 2 hours. And time is 4 hours. So so it would be 120 times. So 2 hours ago it would be 120 times 2, which is a 240. And then another 2 hours ago it would be 240 times 2, which is 480.
Yes.
So the corrected activity would be 480 counts per second.
Yes, that's correct.
Okay. And nuclear fission and fusion are two nuclear reactions which release large amounts of energy. Describe briefly what happens in each case. Um, nuclear fission. Mm, isn't that like when the atom splits?
Into so first nuclear fission is when
Um,
a heavy nucleus splits into two smaller nuclei, and in this process it gives off the neutrons. So basically if there is a heavy nucleus of an atom and it hit by a fast moving neutron, then it splits into two smaller nuclei. This is known as fission.
okay. Um, right. So it's nuclear fission is when a heavy nucleus splits into two lighter nuclei.
Yes, not always two, it splits into smaller nuclei.
Okay, smaller, lighter nuclei. And nuclear fusion is um, so is it when two small nuclei like merge together to form one heavy nucleus?
Yes, that's correct.
Okay. And that's the end of the question paper.
Yes. Now we have to start the next one, the one that I have received yesterday, right?
Okay. Yes. So one kind of so question one kind of earthquake is called an L wave. In L waves, the particles of the material vibrate um, perpendicular to the direction of the propagation. A particular L wave has a frequency of 0.002 Hz and a wavelength of 2,500 kilometers. Um, which one of the following statements about L waves is true? So the particles vibrate perpendicular to the direction of propagation. So are L waves are transverse.
Yes. So the alveolar particles moves perpendicular. Yes, so alveolars are transverse. That's correct. Now,
Um,
explain what is meant by frequency of 0.002 Hz.
um, so um, 0.002 hertz. That's the frequency is the amount of vibrations that pass a fixed point in a second.
Yes.
So it's it means that um, it means that 0.002 um, complete vibrations
It means that this wave completes
pass
0.0002 vibrations in a second, or you can say it passes 0.0002 times in a given second. That's how you can explain this, because it's basically vibrations per second. How many vibrations are there in a second? That will give you the frequency. So if it's 0.002, that means this L wave has vibrated 0.002 times in a given second. Okay,
okay
is it clear?
that the so that the L wave has vibrated 0.002 times per second. Okay. 3. Use the so use the information above to calculate the speed of this L wave. So okay. So we've been given the frequency and the wavelength. So V equals F times lambda.
Yes.
Um, so V equals 0.002 times 20 500 or 2500.
Yes.
So um so that gives 5. V is equal to 5 meters per second.
Yes, that's now part B.
Okay. Um right. Part B. Um So ultrasound can be used to measure the diameter of the head of a baby in the womb. When ultrasound reaches the baby's head at A, some ultrasound is reflected back to the detector and produces pulse A on the CRO. Some ultrasound passes through the head to point B and is reflected back to the detector. This reflection produces pulse B on the CRO. What name is given to the reflection of a sound wave? An echo.
Okay.
Um, Number two, the the CRO is adjusted so that each horizontal division on the diagram below corresponds to a time of 40 microseconds. How long is the time interval between the arrival of pulse A and the arrival of pulse B to the detector? Okay, so each square is equal to 40 microseconds. So there's 3 squares in between pulse A and pulse B. So um, the time interval is 120 microseconds.
Okay. Now
Um,
part C.
Now the next one, number 3. How long does it take for the ultrasound to travel from one side of the baby's head to another? Give your answer in microseconds. Okay. So time to travel from so the time taken for it to travel from B to A. Um, so that's 120 microseconds.
Okay. So time taken from B to A is dash microseconds. So what's your answer?
Wait. So um, time taken time taken to travel from B to A. Um, oh wait. Okay. From B to A. Um,
So basically, if you want to calculate the time, it's by
so it
speed equals distance over time. Is this clear?
um wait. Sorry. What?
Like if you want to calculate the time, you have to use the
Mhm.
speed distance equation, that is speed equals distance over time.
Okay. So time is distance over speed. Um, and the distance is um, so uh, so the distance is
Okay, see, it's given as like the CRO is set so that each horizontal division on diagram above corresponds to time of 40 microseconds. Okay,
Okay.
so first is how long is the time travel between pulse A and B detector. So you have calculated this one as 120 microseconds, right?
Yes.
Okay, then next it's how long does it take for the ultrasound travel from one side of the baby's head to the other. Now you see that means time travel from B to A. It's given as ultrasound travels at a speed of 1500 meters per second. Okay, so
Mhm.
what you have to do, you just have to, okay, leave that as of now. This will be for the width. For this you have to use only this one. From one side of head to the other side, that is from B to A, that
Yeah.
distance. So calculate that distance from this graph.
Um. So the distance is mm, well, there's like three time divisions between it.
Yes. Wait a second. So
Um.
how long is the time travel between the arrival of pulse A and the arrival of pulse B at detector? Give your answer in microsecond as well. Then how long does it take for the ultrasound to travel from one side of baby's head to the other? Give your answer in one. You are advised to show clearly how you get the answer. Time to travel from B to A in microseconds. Okay. From part D, ultrasound has it at speed of 1500 meters per second. So in the previous question, it's given as how long is the time interval between arrival of pulse A and the arrival of pulse B at the detector. So arrival of pulse A and pulse B, it was total 120 seconds, 120 microseconds, right? Now it's in this question it's given how long does it take for the ultrasound to travel from one side of baby's head to other. Okay, that means it's the half the time taken to travel from pulse A to B. Okay,
Okay.
so
So
this is,
half the time taken.
yes, so this is 120 divided by 2, that is 60 microseconds.
Okay.
Because why?
All right then.
Because it was gets
Because it's
reflected, right? So here it's
yeah.
only passing from one point to another point. So you have to
Mhm.
half that.
Okay. Right. For then, ultrasound travels at a speed of um 100 1,500 meters in a baby's meters per second in a baby's head. Use your answer to part 3 to calculate the width of the baby's head from A to B. Um, okay, so distance is speed times time. Um, and time was 60 microseconds. Um, and 1 microsecond is 1 times 10 to the minus 6 seconds.
Yeah, so here you have to use distance as equals to speed into
Mhm.
time.
So to work out how many seconds that is, we need to do 6 times. Um,
And
so
we know it's 60 microseconds, right?
yeah. So okay. So they got 60 microseconds um, by doing 6 times 10 to the minus 6.
Yes.
Okay. So so to and so do we multiply that by 10 to the positive 6?
No. It's width of the baby's head, which means it's the distance that we have to calculate. Distance from one point to another point, that means distance from one ear to another ear. That is basically the width of the head. Okay, like if you see this picture, so this is his head. This is his 1 ear. This is 1 ear. So whatever be the distance between is actually the width of his head. So we have to calculate the distance. We know that the sound took 6 microseconds to travel from A to B. Okay. We know that
Uh-huh.
speed is 1500 meters per second. So we just have to use
Yes.
the speed time equation, that is speed equals to distance over time, and distance is
Uh-huh.
equals to speed multiplied by time. Speed is 1500 and time is 6 into 10 to the power of minus 6. You have to multiply them together to get the width of the head.
Okay. Okay. So you just need to do like 6 times 10 to the minus 6.
Yes.
Okay. So um the speed was 1500 and the time was 6 times 10 to the minus 6. So, so that would be 9 times 10 to the minus 3.
Yes. It's minus 3 or minus
So
2?
minus 3.
Okay.
So that would be 0.009 um 0.009 meters, or no, so that's 0.009 meters, and then we convert that into centimeters
Yes.
by multiplying it by 100,
Yes.
which is 0.9 centimeters.
It's 90 centimeters. Your answer is
90 cent.
0.009 meters, right? So if you multiply
Mhm.
it with 100, you'll get, okay, yes, it's 0.0009 meters, right? Then it's definitely
Uh
not
huh.
9 centimeters. So zero point 0.9 centimeter is the width of the head. Okay.
Okay.
Okay, now for the next one.
All right. For the next one, um, so number 5. Um, explain why it is better to use ultrasound rather than X-rays when monitoring the development of a baby in the womb. Okay. Um, oh, because X-rays are harmful to the pregnant mother.
Yes. Actually, X-ray can kill and damage the cells basically, and that's why it's not recommended.
So it can kill and damage the cells and the fetus.
Yes, like cells basically, exactly fetus you can say. But yeah, it can damage cells, so ultimately it will cause a damage to the fetus. But basically it
Okay.
attacks on the cells. It works on cellular level.
Okay. And so it's harmful to the fetus. Okay. Um, number now question C. Um, the diagram below shows four of the seven members of the electromagnetic spectrum. They aren't arranged in any particular order. Identify the missing members of the electromagnetic spectrum by writing their names in the appropriate part of the table below. Okay, the first one is X. No, the first one is microwaves.
So it's wavelength, so you have to see that which one is the smallest and largest. Okay, so microwave is correct.
Then it's uh, then it's the visible spectrum,
Yes.
and then X-rays.
Yes. So basically they are arranged according to the wavelength. So microwave has the highest
Mhm.
wavelength among these. Then it's visible, then it's X-ray. So like, and their values are given also.
Okay. So next one. The diagram below shows a ray of light passing through a um, rectangular glass block. What name is given to the bending of light when it passes from air into glass? Refraction.
Yes. Okay, now using a ruler, draw the normal at the point where the light enters the glass. Label the normal with the letter N.
Okay, so it would be 90 degrees to the surface of the glass block. Like,
Like definitely where this ray is falling on this glass, at that point you have to draw a normal which is 90 degree to the surface of the glass.
okay,
So like you can see
all
my
right then.
cursor,
Yeah.
it's here and it's here also.
Okay. Yeah. Okay. Um, next one. Mark clearly on the diagram the angle of incidence in air with the letter I. So the angle of incidence in the air with the and mark it with the letter I. So it would be between the first ray and the normal,
Yes,
like the angle between the
yes.
first ray and the normal.
So angle of incidence is basically the angle between the normal and the incident ray.
Okay. What causes the light to change direction in the way shown in the diagram when it passes from air into glass? Um, it enters from a rare medium to a more dense medium, which makes the light um, slow down.
Yes.
So it enters from a rare medium. into a dense medium which causes the light to slow down. Okay, and next number 5, or no, number question B. Um, B1, state carefully what is meant by the focal length of a converging lens. So it's the distance from the lens to the principal focus
Yes.
where the rays um from the lens to the to the principal focus.
Yes. So basically it's a distance from the optical center to the principal focus, or from the center of the lens to the principal focus. It's the focal length.
Okay.
Now it's mentioned then what is meant by the focal length of a converging lens. So like whether it's a diverging lens or the converging lens, distance from the lens or the optical center to the principal focus is actually a focal length. But specifically it's given as that state carefully what is meant by focal length of a converging lens, specifically converging lens. Then your definition should be like that it's basically the distance between the optical center and the focus where all the parallel rays incident and meet at one point after the refraction. Okay,
Where all the parallel rays.
converges at the
Um.
principal focus or converges at this point.
Okay. At this point. Okay. Um. Okay. Next one. Question 2. Um. Describe in detail how you would use a distant object to measure the focal length of a converging lens. In your description, you must state the apparatus you use, describe fully what you would do, and state what measurements you must make to find the focal length. State what you would do to ensure your measurement of the focal length is accurate is as accurate as possible.
Okay.
Okay. So starting off with the apparatus used. So we need a lens. Um, we'll need um, a lens, a screen, a white screen,
Okay.
um, a meter rule,
Yes. Or simple ruler.
okay, um, a and you need a distant object like a tree or a window.
Yeah, any object, yeah, a distant object.
Um, okay, that's the apparatus. Um, next, we need to next describe fully what you would do. Okay, so move the lens. So move the lens or the screen until a sharp image of the distant object um, is formed.
Yes. So until a very clear image is formed. Yeah, we can say sharp image or very clear image is formed.
Okay. Um, then you need to the measure the distance from the screen to to the
Lens.
lens.
Yes.
Yeah. From the screen to the lens. Um, and then what you would do to ensure your measurement of the focal length is as accurate as possible. So you need to take repeats
Yes. So like for every
2 to 3
experiment,
times.
is for every experiment, if you want a better accuracy, you keep on repeating the experiment and take the average. Okay. So this will give
Okay.
you a more accurate or nearest to accurate.
And calculate an average. Okay. Next question then. Um, so C. The full-scale diagram below shows a converging lens and an object. Each principal focus is marked with an F. Um, Using a ruler, carefully draw two rays on the diagram to find the position of the image. Okay. So let me get a screenshot of this and
Okay.
okay. Um, so using a ruler, carefully draw two rays on the diagram to find the position of the image. Okay. So first, a ray like that's parallel to the axes, um, and then
Okay, so you draw this. I'm just coming within
okay,
2 minutes. Okay.
okay. Um,
Okay, I'm back.
yeah. Sorry. I can't seem to like rotate the ruler. Um,
Okay. So
um,
basically, okay.
I'll try it in paint.
Okay. So you're doing it, right?
Yeah, I'm doing it. Okay, so right. So the ray that's 90 that's parallel to the axis.
Yes.
Um, and then ray that goes through the optical center.
Yeah. So one is parallel to the axis, and then after refracted
Um,
from the lens passes through the focus or principal focus.
yeah. Okay.
And for the third ray, because you have to take three rays.
Okay. So the image formed will be beyond f,
Yes.
and it'll be inverted and magnified.
Yes, that's correct.
Okay. Um, right, so calculate the magnification of the image in your ray diagram. Um,
Like since you have drawn this on paintbrush, I don't think so you'll be able
mhm.
to like calculate the exact centimeters and all that. But you can take a general measurement. A general in the sense like how can you take that? You can just calibrate your y-axis, label your y-axis, taking equal intervals. That will help you to calculate the length of image and object.
Okay. Okay, so um, it's so on Paint. It's the image 13 is 13 boxes across the principal axis, um, and
And for image, it's image that you're telling me or for object?
the image.
Okay, and for object?
Um, so and the object is um, that's 11 boxes behind the lens, so across the
Okay, so
principal axis.
you're measuring in x-axis, you have to measure in y-axis because you want to calculate the length. Okay, it's height basically. So if it's height, so you have
Okay.
to measure the y-axis.
Okay. Okay then. Okay, so the image is 9.5 is a 9.5 boxes high, and the object is 4 boxes high.
Okay, now divide them.
Okay.